variation of parameters. So what is this about? Well, this is just a continuation of what we just finished. Okay, the method of undetermined coefficients. However, let's recall that the method of undetermined coefficients, which we just finished, is again limited to constant functions, polynomial functions, exponentials, e to the ax, sine, cosine, or products, combinations, sums, products, or well, not that division, sums or products of the aforementioned functions. And we actually excluded these functions right here. All right. So here's the thing. Now, with variation of parameters, we're going to design a method to actually be able to solve differential equations where the input function, the right-hand side of the DFQs, are these kind of functions like logarithmic functions, the remaining four trig functions, rationals, or combinations of these ones. All right. Okay. So for the method of solution, so guys, at this time I typed the whole thing because I think I'd rather explain this as a matter of a presentation rather than writing all of these U's and Y's and subscripts and primes and all that. Okay, so here's the thing, guys. So let's get started with the derivation of the method. Okay, so number one, we want to solve the differential equation. Again, y double prime plus p of x, y prime plus q of x, y equals to g of x, okay? So, well, actually, we are going to solve this differential equations for constant coefficients, okay? Constant coefficients. So what are we going to do? Just like undetermined coefficients, we're going to solve the corresponding homogeneous equation. All right. I mean, set it equal to zero and use the three different cases. That's not going to change. All right. And the solution will be of the form, C1 y1 plus C2 y2. To well, unless it's a higher order, well, C3 y3, C4 y4, etc. But actually, for this method, we're going to limit for order two. All right. You're welcome. All right. Mhm. So number two. Okay, guys. So for the particular solution, remember how we had different cases, like if we have a quadratic polynomial, we need the entire quadratic generic polynomial. Well, this time we're going to assume a particular solution of the form y sub p equals u1 y1 plus u2 y2, where this time, guys, u1 and u2 are no longer constants like the previous case. Remember, these were constants to be determined? No. This time, u1 and u2 are functions to be determined. All right. How are we going to determine those functions? Well, we need a couple of tricks here. Number one, this is going to work with the following condition, with the condition that y prime sub 1 times y1 plus y sub 2 prime times y sub 2 equals to 0. Don't ask why for now. Maybe not ever. Just go with the flow. Just go with the flow of what. Well, maybe later we get to explain why do we make this equal to 0. Well, that's actually the variation of the parameter, right? The parameter we vary it in a way. And number two, well, of course, y sub p, because it's part of a linear combination with y sub c, that must satisfy the differential equation. All right. So okay, so that means we're going to work with this y sub p. So actually, I'm going to abbreviate this guy right here. Y sub p equals just u1, y1 plus u2, y2. Notice I abbreviated everything in the following steps to avoid having too many parentheses, too many x's. I mean, it should be understood that everything here is a function of x. Well, maybe a function of t or whatever the independent variable is. Okay, so let's find the first derivative of this. Well, we need one product rule here and another product rule there. So the derivative of this first product, that'll be u1 prime times y plus y1 prime times u, which is these two terms, right? Let me actually highlight the result of this product as I go. Okay. And then the derivative of this second product, that'll be u prime 2 y2 plus u2, I mean, plus y prime 2 times u2, which is with a different color. Let me highlight that. All right. And guys, let me group this, let me group some terms. Let me do some grouping of terms. So actually, I'm going to group, let me erase all this, and I'm going to group with a different color, u1, y1, and u1 prime, and then u2 prime, y2. Actually, these two together. Why am I grouping this? Because that's one of the conditions we stated here. This guy is going to go to zero. That's actually, again, the variation of the parameter, if you will. Okay. Okay. So that's going to leave us only with this right here. Okay. Let's find the second derivative. So differentiate this guy. So we need another product. Okay. Another product rule, another couple of product rules. So the derivative of this product will be all this here. And then the derivative of the second product will be all this here. All right. Do you guys agree with that product, with those two product rules? Okay. So u prime y u1 prime y1 prime, yes, plus u1 times y1 double prime, same over here. All right. So now that we have the two derivatives, how about we substitute into the differential equation? Okay, but the question here is, why do we substitute that into the differential equation? Because that's the second condition. This guy, along with the two derivatives, is going to satisfy the differential equation. Okay, so what are we doing here? Okay, let me get rid of all this highlight. Let me highlight once again with different colors. So the first derivative, the sec goes into the first derivative. The second derivative, it's all this, all right? And then the original function, which is this guy right here, just substitute in there, all right? So what are we gonna do next? So next up, it's to distribute. Distribute the P over here and over there. Distribute the Q over here and over there. And that's going to give us all these terms right here, right? PU1 Y1 prime, PU2 Y2 prime, and then QU1 Y1 plus QU2 Y2. All right? Okay. So what are we going to do here? Okay. So in this next line right here, we have a bunch of terms. What do we do with all of those two terms? Number one, so I'm going to highlight with green all terms containing U1. Okay, U1, whoops, highlighter, U1, another U1 here, and then another U1 here. All right. And with pink or red, I'm going to highlight all terms containing U2. That is U2 here, U2 there, and another U2 term here. What are we going to do with those terms? We're going to factor out precisely U1 in the green group, which will be all this, and U2 on the second group. All right? Are you guys following me here up to this point? Is everything making sense? I know it's a lot of symbols. There's no numbers at all other than the subscript, but well, thanks. Okay, that's great. So let's reduce this. How about okay? How about this guy right here? Okay, maybe this guy equals to zero, and that guy is also equal to zero. Why is that? Because doesn't that look like the form of the homogeneous differential equation? So this is the thing, guys. Here's the thing. When we solve the homogeneous differential equation, we get a linear combination of a fundamental set of solutions, of two solutions, y1 and y2. So that means this equation is true for y1 and also true for y sub 2, right? So that's why we can set that those two terms equal to 0. All right. And this is because uh, y1 and y2 are solutions to y double prime plus p, y prime plus q, y equals to 0. All right. That's why. Okay, guys. So what is that going to leave us with? That's going to leave us with this equation here. Let me box it. Let me actually label this equation as equation number 2. But what's equation number 1? Equation number 1, it's the condition here, the variation of the parameter condition we set at the beginning, right? So we're going to form a system of equations, of linear equations, this system right here. But in this case, notice it might be a little confusing because which ones are the unknowns, okay? So at this point, y1 and y2 are known. U1, I mean u1 prime and u2 prime are the unknowns. So how do we solve that system of equations? Well, there's many methods, substitution, elimination, but I actually chose to use Cramer's rule for a big reason. Remember, okay, be honest, guys. Do you remember Cramer's rule to solve system of equations? Okay, let me give you a numerical example. Okay, let me give you a numerical example at the bottom. Yes, I'm already spoiling the result, but just pretend there's nothing there. Okay, just whatever you saw, just unsee it. So 3x plus 5 equals to 7, 5y. 5x plus 4 equals to 4y equals to 6, for instance. So solve a system of equations using Cramer's rule. We need three matrices and find the determinants of those three matrices. So number one, we need the determinant matrix. We call it delta, which is a matrix with the coefficients of the variables 3, 5, 5, 4. All right. And then we need another matrix, another determinant, delta subscript x, or sometimes we just call it delta x. What do we do? Replace the first column, which represents the coefficients of x, with whatever we have on the constant sides. That is 7, 6, and then 5, 4 remains the same. And then another delta y, which is the x column remains the same. Replace the y column with 5, 4 with the constant coefficients. All right? Does that ring a bell from back in either pre-calc or college algebra? Hmm. Okay. Okay. We can talk about that later. Okay. I see. So now let's go back to this. So here, our our delta, it's going to be, first of all, again, the unknown functions or the unknown functions are, okay, no, the coefficients. So that is going to be uh, y1, y2, y1 prime, y2 prime. Delta, well, in this case, there's no x and y, right? Because our unknowns are u1. Delta u1 prime will be, okay, so that'll be 0 g of x and y sub 2, y sub 2 prime, all right? And then delta u sub 2 prime, that equals, keep the same first column, y1 prime, and replace 0 g of x, okay? How do we calculate the unknowns? That is delta u1 prime over delta and delta u2 prime over delta. Okay? And let's work with these determinants here. Well, and again, guys, the purpose of using Cramer's rule, it's because Cramer's rule will spawn a very special determinant. Remember the determinant? Remember the Wronskian? Okay? So the Wronskian. So How do we evaluate these determinants? Okay, so again, product along the main diagonal minus product along the second diagonal. And I even typed the zero here so you can see how this cancels later to zero. And divide by whatever you get here as well. But again, this is the Wronskian. And then the Wronskian is something you can calculate on the side. All right. Same here. Y1 g of x minus 0 y sub 1 prime divided by the Wronskian. All right. So after simplifying this to 0, we're gonna be left with these two equations. Okay. What is that? U1 u sub 1 prime equals to this, u sub 2 prime equals to all that, all right? Well, so this will give rise to two separable equations. I'm going to change the notation u prime to du dx. I'm going to multiply both sides by dx on both equations. And what do we do once we separate the variables? Integrate both sides, all right? The integral of the u1 will be u1. The integral of the u2 will be u2. And this is how we find these coefficients, which again are no longer constant. You can see these are integrals, which may give us constants as final result, maybe, but actually these are going to give us functions of the independent variable. All right, guys. So now, putting all of these together, let's have a look at the definition below. If the non-homogeneous equation y double prime plus p of x y prime plus q of x y equals g of x has a complementary function y sub c, okay, or rather solution. I should have said solution, I think. This is what you already know how to get. C1 y sub 1, C2 y sub 2 from the previous cases a couple sections ago. Then the particular solution y sub p, now u1 y1 plus u2 y2 will be y1 times the first integral plus y2 times the second integral that we just derived here. All right. So in other words, guys, what do we need? What do we need to get this done? Number one, we need to solve the homogeneous equation just like in undetermined coefficient. That's the exact same, considering all the same cases. That's okay. And number two, we will need to take the Wronskian of those fundamental solutions you get from the homogeneous equation. That is going to be the denominator of these two integrals that we are set to evaluate when solving an equation like this. And well, we need to keep in mind what g of x is, which is going to be part of the integrands in our later solution to the differential equation. Okay, so unfortunately, I don't think we're gonna get the chance to solve one example because these are they're not that long, but I don't want to rush through the I don't want to rush through this.